Hey everyone, good evening. So, I hope you will be able to hear me. If you can't hear me, please let me know. So, I welcome you to the rocket propulsion course. I will be I will be conducting the tutorials for you. So every week we'll be having this interactive sessions where you can come and ask any questions if you have, and we will also be solving few questions in front of you so that it will be easy for you to attend assignment problems. So that is the main focus of this session. But please feel free to interact, ask questions if you have any, and also if you have any you know. Uh, doubts regarding the lectures, you can ask me. Uh, so, uh, so let's say to introduce myself, um I am Ganesh Kumar. I am a PhD student. I am actually a fourth year PhD student at IIT Gandhinagar. So, uh, m- basically, my focus is on rocket propulsion. In specifically, my research focuses on predicting performance, especially propulsive performance of solid rocket motors. But particularly, I deal with a few novel propellants, not the conventional propellants. I try to find out what is the performance issues with the propellants and how can we improve it. So that is my research work at here at IIT Gandhinagar. So it deals with a lot of different various areas of study, includes rocket propulsion, computational fluid dynamics, multi-phase flow, turbulence. So it includes all these important aspects into my model. So um, in this course, what we will deal is it's a basic introductory course to the rocket propulsion. Um, uh, this is actually an important course, especially if you are interested in you know uh, trying to uh, improve your skills in terms of rocket propulsion, and if you want to embark on a career in rocket propulsion or related fields. This is one of the basic course you must take, and I think everyone is interested in that, and that's why you guys are taking this course. Uh, so um, yeah, so I am here to guide you. Feel free to switch on your cameras and mic, and if you have any questions, you can ask me. So we have few questions in the chat here. So we have any YouTube channel or recorded lecture for this. So I guess recorded lectures is already available to you. Uh, so as soon as this session is over, I will post all these videos in a YouTube channel, and I will I mean in a YouTube, and I will share the link also. Usually, you can access this link from your NPTEL page. Okay. Uh, Once you log into your forum, there will be a separate session called problem solving session, and if you open it, there will be a link to Google Sheets, and in that Google Sheets, I will be keep updating the both the notes and also the videos, recorded videos. Uh, if you want, you can go and look at it. Okay. So, having said that, we have around 27, 28 people here. So, uh, do you guys have any questions before I start? Do you have any uh, doubts you want to ask, or if you have any other questions, I'm here to answer you. Is there any questions, or do you want to share anything? I see a huge silence here, which means everybody is on the same page. Feel free to interact. Feel free to stop. Uh, anytime in between. Okay. So yeah, Avinash is asking if possible, please share via mail. It would be helpful. Uh, Actually, you will be receiving, I guess, a mail containing this sheet you can bookmark it and you can use it. So that is the sheet I'm going to update it, right? So you will soon will be receiving from NPTEL side. You don't need to worry about it. Okay. Any further questions? If there are any questions, maybe I can wait for 1 or 2 minutes.
Sir, you're from IIT Gandhinagar, right?
Yes, yes. I am from IIT Gandhinagar.
I think you are from IIT Madras, PhD.
So I am from
Oh,
IIT Gandhinagar. But yeah, the professor is from IIT Madras. The professor who is teaching this lecture is from IIT Madras. But I am associated with IIT Gandhinagar. I have a separate supervisor here, PhD supervisor here. All right. So, okay. Vaishnavi asking, sir, can you please explain the concept of flame velocity and burning velocity? Okay, it's a completely, uh, yeah. I think it's related to combustion. Maybe Vaishnavi, you can stay back a little bit. We will complete this related to rocket propulsion. We'll complete uh, you know, the question, and then we'll come back to your question. Okay. All right. Any other question related to the lecture materials and assignments shared? Let me quickly check my recordings. Okay. All right. So if there are no questions, I have a question. I have one problem here for us to solve, and it is going to be primarily done by you. I will be here asking you questions continuously, and uh, let's make it interactive so you can also answer me the question. Okay. So I hope you guys went through the first week lectures. So it deals with motion in space, and I think the second one was related to frame of reference, where you must have learned orbital velocity, centrifugal force, pseudo force, and velocity requirements. Basically, what is basically what we why do we call delta V, right? So those things you must have studied in your first week of lectures. Um, the motion in space basically deals with basically physics. So, Aishwarya Ranjan, do you have any questions you wanted to ask? Okay, so maybe by mistake he or she might have turned on. All right. So I have few more questions also here in messages. How to calculate landing position of a rover if the planet is continuously moving? Okay. Yeah, we'll come back to it soon, Somasiva. And Tushar is asking this question is concept is related to frame of reference. Oh, I see. Okay, you guys are asking from frame of reference. All right. So we'll come back to this questions soon after solving this session. The reason is if I once I solve this session, I mean once I solve this problem, uh, uh, after that we will have enough time for us to discuss and then you know exchange questions and solutions. Okay. So let's quickly complete this problem and then we'll discuss. Um, so as I was telling, you must have learned about basic physics concepts like impulse, force, and what else? Momentum, rate of change of momentum, and how are these uh, how are these concepts helpful towards propulsion? And also in the second chapter you would have learned, I mean second lecture you would have learned the orbital velocity, velocity requirements, and all those things. So these problems actually deal with velocity requirements and how to calculate that for any mission. Okay. So let's get into the problem. The problem, mm, It has only three subparts. We are going to just find these three, but it is going to give you a lot of physical insights. So the problem goes like this: the Pegasus rocket is launched from a jet aircraft at a height of 15 kilometer above the surface of Earth. So basically, any rocket is launched from the surface of the Earth. So this is a kind of unique rocket. What they do is they first go to a 15 kilometer. I mean, they carry the rocket and they go to the altitude of 15 kilometer, and from there they launch it. Okay, and assuming the rocket is required to place a satellite in a circular orbit at a height of 500 kilometers. So from the rocket has a satellite, which we call it as payload, and it has to place that satellite in the orbit of at a height of 500 kilometers. So from 15 kilometer it has to go to 500 kilometer. Okay, and you can assume the cruise speed of aircraft at 15 kilometers. So aircraft is only going to launch the rocket. So there's going to be a velocity for aircraft also, which is 220 meters per second. So this is the velocity with which aircraft is moving. Okay, and one more thing is given is the mass of satellite is 500 kg. It may not be required for this problem, but let's see what we can do with this. Okay, so determine what we need to determine the velocity to be provided by the rocket to reach the orbit. So one thing is how much velocity or velocity requirements in this case needs to be provided by the rocket to reach the orbit, where the orbit is at 500 kilometers. Okay, and velocity to be provided by the Pegasus rocket to make the satellite stay in the orbit. So which means like once if you reach the orbit, it's not going to stay. We are going to see about it. So to make it stay in the orbit, you need to have a some radial velocity. So in terms of orbit or in horizontal velocity. Okay, and this is the total velocity requirements of the rocket. So the main aim is to place the satellite at 500 kilometer altitude. Okay, um, let's uh, let's see if I can draw some schematic of it. During this time, if you have any questions, please feel free to unmute yourself and ask. How how do we draw this? Let's say we have Earth here, then we have orbit somewhere here. Okay, just exaggerated the orbit, but I guess you guys can understand. So basically, it is at a height of 500 meters. Let's see, 500 kilometers. This is orbit, and there is a plane flying. Okay, 'kay. From here you are launching the rocket. Let's see whether I can launch the rocket from here. Okay, so this is the plane rocket. This is at 15 kilometers. Okay, so yeah, this is a crude way of visualizing it. Uh, is cruise speed and maximum speed are same? Well, uh, the cruise speed is nothing but the speed at which you know in any aeroplane, if you take off you know, if you once you take off, it goes through a certain altitude and it just moves with a constant, more or less constant velocity at that altitude. You know, you must have heard that uh, the captain telling that we are cruising at a altitude of this many kilometers, right? So cruising means like you are not changing the velocity much, or you are trying to maintain the stable flight configuration and stable velocity. I mean, almost like stable only. So uh, that is what we call it as cruise, and the phase is called cruise phase. So basically, uh, as the flight takes off, it is going to, let's say it is taking off from some place, from place A, and it is going to place B. So it's going to take off. This is going to be a takeoff phase, and is going to land here. This is going to be your landing phase, and in between this is nothing but a cruise. Okay, so that is what it means. Cruise speed means it's not actually a maximum speed. It's just the speed with which airplane is moving. That's all. So I hope that answers your question. So now coming back to the question, is there? Can you guys guess why we need to launch the rocket from an aeroplane at a height of 15 kilometer instead of launching it from ground itself? Why people must have did this? Any idea? To save fuel. Okay, it requires less propellant to launch, uh, to reduce work done, so that it has some initial velocity component. Actually, it's quite surprising that you guys all are right. Actually, that is what we are going to find out. So we are going to reduce the work done, and we have some initial velocity component. Yeah, less air resistant at higher altitude. So air resistant at a higher altitude could be a reason, but that is not our main focus when we are in rocket propulsion, when we are launching a rocket. So we need to take care of its effect on the structure. So those things are required. But basically, what happens is your delta V requirements goes down. So that is what we are going to see. So I am surprised that you guys guessed it right. So let's look at the let's solve the problem and try to quantify what it exactly gives. Okay. Uh, let's say if I want to write it in words, in a simple words. So the goal is to launch satellite from 15 kilometers to 5 kilometer. Okay. Now what is the velocity required to just reach that orbit? Let's say if I'm just firing it, what is the velocity requirements? Velocity requirements, why we talk is basically we are trying to find out how much energy I need, right, in order to reach from 15 kilometer to 500 kilometer. So just to reach, uh,
Sir, we equate gravitational force and centrifugal force.
We equate gravitational force and centrifugal force. Okay. So why do we need to do that? Gravitational force and centrifugal force. But we need to find what is the velocity requirements, right? Or in other words, if I want to put, uh, let me put it in this way. What is the energy required to take the satellite 15 kilometers to 500 kilometers? So Bharat is telling orbital velocity, okay, and Prajwal is telling RE plus 15 to RE 500, yeah. But what are we trying to do here? So what is how do we calculate the energy required to take the satellite from 15 kilometer to 500 kilometer? Overcome the gravitational force. Exactly. So what is how do we do it? How do we exactly calculate that? FDR. Okay. FDR.
Sir, Z M1 M2 by R.
G m1 m2 by R. M1 m2. Is that what you're telling?
Sir, potential energy minus Z M1 M2 by R.
You mean minus Z m1 m2 by R. So how do you write potential energy? So basically you are right, but uh, we have few more also. Integration of gravitational force F equal to gravitational force taking radius as infinite. Okay, yeah, everyone is right. So how do I represent the gravitational force? Whatever I think Gudu said, he's also right. How do I represent gravitational force? How do I write here? So someone said integration. So I need to integrate the gravitational force from 15 kilometer to 500 kilometer, right? Because my force is going to keep on vary as I increase the altitude. It should be R2, not R. Okay, R square. All right. We need to integrate it, dr, right? So, and as Prajwal said, we are going from a radius of Earth plus 15 kilometer to radius of Earth plus 500 kilometers. That is also right. So, please understand why are we doing this? Why are we doing this integration? Because the gravitational force, so the gravitational force F is equal to G m1 m2 by r square, right? Here, so this force is a function of r. It's a function of radius where r is nothing but re plus h. And as you go from 15 kilometer to 500 kilometer, this r is going to keep on increasing, right? So this force is going to be keep on changing, and we need to take that into account. So gravitational force will be keep on changing. So that is the reason we are doing an integration across the radius, okay, or across the altitude. So I hope this part is clear. Nothing F times dr, as Crimson said before, it is going to be the energy, basically energy. And in rocket propulsion, what we usually do is we calculate all these things in terms of velocity requirements. What is the delta V I need? What is the delta V I need? So this is kind of like a instead of telling I need this much joules, people always like to take in terms of this much delta V I need. So that is the reason we are going to change this E to a uh, kinetic energy. So basically, let's just find out energy, and then we will try to find out the velocity requirement so that you will not get confused. So what is this m1 and m2? M1 can be mass of Earth, and M2 can be satellite. Okay, so you are trying to move the. I mean, you are trying to put the satellite into orbit, right? So that is your goal, and we are trying to find out what is the energy required for that. Okay, the way we are trying to achieve, we will study about it in the during the course. So that is where this course is. But we first need to know what is really the goal of this exercise, right? So what is our goal is to put the satellite at 500 kilometer. So for that we are trying to find the energy requirements. So let's say if I plug in all those values and give you the, I guess I have it here, 6378.1 kilometers, and the mass of Earth is also 5.972 into 10 power 24 kgs. Okay, so let's say, and also g is a gravitation universal constant. It's going to be 7 into 10 power minus 11. So Newton meter square. What is the unit for g? Anyone? Let's see who remembers. All right. So we have Somasiva telling Newton meter square by kg square. All right. Crimson also. Very good. So let's put all these things here. And did anyone find the energy here? So it's just straightforward integration, right? So how can we write this? We can write this as GME, mass of satellite, divided by r square dr, interval from RE plus 15 to R. So ME, MS, everything is going to remain same. So I can take these outside. Then I can write this is going to be 2 by R, maybe minus, right? It's going to be RE plus 15 and RE plus 500. So if I substitute it here, then I can write this as 2G MEMS. So it's a straightforward integration. That's why I'm not explaining this. I hope you guys are doing with me. So if you have the answer for energy, please let me know. So we can write this as RE plus 15 minus 1 by RE plus 500. So this energy is going to be basically what is the potential energy, or what is the energy I need to give in order to raise the potential energy of a satellite at 15 kilometers to 500 kilometers. Does anyone have an answer for this?
said integration of 1 by r square dr cell r to the power minus 1 by r.
Yes, sir. Not minus 2, minus 1, I think it will be.
So what is the answer you are getting? Hope it's correct. Ah, yeah, yeah. Sorry. Integration should be minus 1 by r. That's right. So did you guys put the values here? Let's say ms. Okay, this came out as final answer. It's correct. Okay. Does anyone? Okay, you directly found the v. Okay, that's nice. 2.9 kilometers per second. Any idea, Tanisha? What is the energy? So I guess it's around 500 kgs, the satellite weight. Right. And divided by 63788.
I'll actually equate energy with kinetic energy.
Okay. Yeah, we are going to do that. But I just want to show what is the energy coming out. Is that what you're asking, Tanisha?
It's about 4.4 megajoules, I guess.
4.4
Megajoules of the order.
joules. Okay.
So can you show me the last slide?
Plus 500. I hope you guys took care of signs. These are in kilometers. So let's say I can multiply it by 10 power minus 3. So so some people are getting 4.4 megajoules. That's I hope others are also getting the same thing. Uh, so but every time talking in terms of joules is kind of little bit difficult, especially when we have a uh, when we are dealing with propulsion systems. So that's why people always recite to a velocity requirements. So what they usually do is it's a kind of representative velocity velocity which is required, or basically it's a kind of energy which is required to do this operation. So what they do is they take this energy which is equal to half mass of satellite times v square, and this v is going to be the velocity requirement for this operation, like reaching the orbit. Okay, basically the potential energy you are trying to give. So let's say if we do that, we can write v is equal to 2 times e by ms square root. Okay, and let's say if we calculate that, 10 power 6 into 2 divided by 500 square root of answer. So that mm, maybe should come around 2.9 kilometers per second, as Tanisha said. So is it coming around that?
So mass of the satellite I'm unable to find. What is it?
It's 500 kgs.
500 kg. Okay.
Mm.
Thank you.
6 3 93 minus 1 divided by 6778.17. So when I just simply calculate this, I am getting around 17. How much is this? 1770.5 megajoules, something like that. Also make a lot of mistakes. So let me know if this is wrong. So then if I do it, I'm getting velocity like 2.66 kilometers per second. So basically around Tanisha's value. So you guys also getting this? What is the energy or velocity requirements you guys are getting? Any other answers? Hmm. Yeah, so actually this is also wrong. I'm also getting around 296 and this is around
So it is 2.1. I mean,
0.1 gigajoules.
yes, sir, gigajoules. Yes, sir, gigajoules.
So yeah, so this is how you deal with it. It's a very big number, and dealing with this
Yes,
kind
sir.
of big number, it's a difficult, right? So that's why people go and use velocity requirements. So they tell what is the delta v I need to reach the orbit. So that is the reason we convert this into a delta v. Okay, so when I talk in terms of delta v, I get around 2.9 kilometers per second. So which is you know easy to use compared to gigajoules, megajoules kind of usage. Remember, this is just the potential energy. If you just increase the potential energy of a satellite, it's not going to stay in the orbit. Can it stay in the orbit? So, what are the things required for an orbit? If I want to place a satellite at an orbit, what should I do?
The force should be balanced: gravitational force and centrifugal force.
Centrifugal force. So, can you repeat? Are you telling that we need centrifugal force?
No, sir. If the satellite is stationary in any orbit, so it should be balanced gravitational force and
Oh,
centrifugal force.
okay. Yeah. So, yeah, you're right. So we need to. So there's going to be some gravity acting on the orbit, uh, gravity acting on the satellite in that orbit. We need to, you know, develop a centrifugal force. So, but how are we going to do it? So, what is that centrifugal force? How it is coming?
Sir, by giving some velocity,
By giving some velocity, and that velocity
yes,
is going to be tangent to that orbit. So, Basically, the concept is, I hope this way you can understand it better. So, let's say you are standing on top of the hill. Okay, let me draw a hill here. Let's say it's around like 10 kilometers height. Okay? And in this point, what you are doing is you have a stone here, let's say at some mass, and you are trying to throw it out. Okay, with some velocity. So what happens? You just throw a mass out. Any answers?
Maybe sir, this goes under free falling. They goes near to
On a
surface.
parabolic path, it will fall like a projectile.
So yeah, both of them are right. It is going to be fall. It will fall and it will stop at some, at some place, right? So this is what is going to happen, because what happens is there is a gravity acting down. This is the gravity force we say, right? Now, if you try to increase the velocity, let's say I am throwing at a different velocity, additional velocity, then what happens? Say I'm throwing at v plus dv, then what happens?
Its range increases.
Right. So what happens is it will go and fall a little farther away, right? Travels more, exactly. So it's going to, or you can also say, as he said, it's going to, the range is going to increase. Instead of dropping here, you will drop it here. And uh, while this is going on, um yeah, so coming back to that, so if I keep on increasing this, let's say in addition to it, I add a few more v's. So let's say this is a little bigger v, and then I add another bigger v. So I keep on adding it, okay, and up to a certain point, what happens? This surface won't be flat anymore, because the ranges will be keep on increasing. And what happens? You will throw at, let's say, India, and it might go in the center of India somewhere in uh, I don't know what is center of India. Let's say you are throwing it from Mumbai, okay. Yeah, it is not center of India, but anyway, you are throwing it from Mumbai on this side, and what happens? It goes and falls on the other side. Like, let's say it falls in the Bay of Bengal, and if you keep on increasing it from Mumbai to Bay of Bengal, it is, the surface is not straight; it has curved, right? Because Earth's shape is a globe. So this representation is not good. What we do is we'll change the representation. Now we have something like this. Okay, this is where we are standing, and this is our hill, and what we are having is we have stone and we are throwing it out. Okay, now as we increase the velocity, the same logic, let's say we'll keep on adding, we keep on increasing the velocity. What happens is it's going to go and fall farther and farther. Okay, now at some point, this this will, what this will do is, let's say it goes and it's outside this plane anyway. Okay, at some point what happens is this thing is going to keep on rotating, and then it's going to come back, and then it's going to come to the same place again. So if you keep increasing this velocity, so what essentially you are doing is, this gravity, whatever gravity acts in this place, pulls the stone down, but you have given enough initial momentum such that as it pulls down, the curvature of the earth also change the same amount. Let's say, for example, from here to here, let's say it pulls down by 5 mm, okay, or 5 meters, and the curvature from here to here also changes by 5 meters, curvature of the earth, right? Then what happens? The distance between the earth and the orbit is going to remain same. The distance between the earth and the stone is going to remain same, and that's why we call it as at some altitude. Let's say at this point the stone is revolving at 10-kilometer altitude. So basically what we need is, we need to have this initial momentum. We are talking here, we need to give this big velocity in order to make that satellite stay in the orbit. Okay, and that velocity is nothing but the orbital velocity, which you guys already know how to calculate. So basically in the orbital velocity, some people have told that centrifugal force has to be balanced by the gravitational force. So basically, um, what is this centrifugal force? Let's say if you look at it from the stone perspective, this is the stone, and it is keep on getting accelerated by the gravity towards the earth. Okay, but the stone is never fall down because it already has the initial momentum, right? So from the stone, it doesn't know what is keeping it in rotation, and that is why in order to explain it, we add a centrifugal force, right, which is a pseudo force, which is nothing but equal and opposite to a centripetal force. And this centrifugal force is going to be m omega square r. I guess it's m omega square r. Okay, that's when you balance these two, right, you will be able to get a perfect orbit. Uh, so especially we are talking here about circular orbit. So that is what we need. So we need to have this additional centrifugal acceleration also, in addition to so basically this force is also going to take some energy, and that energy also should be given by the rocket. So rocket's main goal is not to just reach the orbit, but also give the initial momentum to that satellite. So I hope that's clear, because the satellite has to stay in the orbit. It doesn't want we don't want it to come and drop it down to earth, right? So that is what the second question is asking. What is the velocity provided by the Pegasus rocket in order to make the satellite stay in the orbit? So what this essentially means is, we need to calculate the orbital velocity, right? That is what it means. Is that clear, the concept?
Yes, sir.
All right. So let's try to find out the second part, the energy required to keep it in the orbit, which is going to be which is going to be m into v naught square by 2. This is the orbital velocity. Okay, so how do we find orbital velocity? Orbital velocity, we have some formula. If you know, you can tell me the formula, or we can always derive it. It's not a big deal. It's nothing but gravitational force is equal to the centrifugal force, as we discussed, right? So it's going to be g m e m of satellite divided by re plus h square, I guess, is equal to centrifugal force is going to be mass times omega times r square, right? And we know v naught is equal to uh, r omega, or is it right? Yeah, r omega. And let's say substitute it here, so we can cancel this ms, and to be simply, let's not write it here. This is also going to be r plus h, right? This is at the what do you call, the orbit. It's what we are trying to calculate. Check whether I'm going in the right direction or not. All right. So then, what we are interested? We are interested in me by re plus h square is equal to omega into r plus h is nothing but this is also r plus h. Anyway, I hope you can understand it. So it's going to be v naught into r plus h, right? So and we need v naught. I mean, what is centrifugal force? Omega square r, right? I'm something else. You guys are also just listening. It's going to be omega times r plus h, and r is nothing but r. Okay. What else you can write? You can write this as a so v naught square by reh is going to be omega square times reh. Right, v naught square is omega square reh divided by reh will be like this. So then you can write this as v naught square by re plus h, and then you can cancel these two, and then you can write v naught is square root of g me by re plus h. Okay, alright, so much you already told. So let's just find out the orbital velocity. So how much is it coming out to be? Mass of Earth is 0.572 into 10 power minus plus 24 divided by RE is going to be 6378.1 into 10 power 3 plus 500 kilometers, which is also 500 into 10 power 3, which is this. Okay,
So
7.6.
it's 7.6 kilometer per second.
Thank you, Akileshwar and Tanisha. 7.6 kilometers per second. So this is the orbital velocity, the velocity with which any object actually. We in here we didn't substitute. You must have noticed we didn't substitute the mass of the satellite. So which means like whatever be the object there, the velocity is 7.6 kilometer per second in order to make it stay in that orbit. So whether it is small or large, it's going to be the velocity requirements is still the same, or the orbital velocity is still the same. Okay. Now the third question is, what is the total velocity requirements? So one is to have this orbital velocity. So yeah, can you explain why sidereal day occurs? Okay, we'll come to that question soon, Somashiva. Uh, so one is one. So uh, how do I say this? So, so for a rocket, there are two. Basically, you want to keep a satellite into orbit, and also you want to reach the orbit. So there are two requirements, right? There are two uh, goals for a rocket, or it's like need for the rocket. So if you combine these two, what is the total velocity requirements? Is the final question. So how do we calculate it? Basically, it comes from energy only, the total energy required, and we just put msvt square in order to get the total velocity requirements. So this is going to be partly from the gravity or amount of energy you spend to increase its altitude from 15 to 500 kilometers, and also potential energy. It's right. So potential energy is nothing but how much sorry, one potential energy plus kinetic energy, how much kinetic energy you require in the orbit in order to make it stay in the orbit. All right. So the potential energy, we all know it's going to be GME, mass of satellite, by r square dr, re plus 15 to re plus 500, plus kinetic energy is going to be simply ms v naught square by 2. So if we do this, it's going to be simply you no need to have the mass of satellite here. Okay, and we can simply write the total velocity requirement for this is going to be, I think we already found this. Let's see. It's going to be v naught square plus 2gme integral of re plus 15 to re plus 500 by r square dr, the whole square root. So this is the total velocity requirements. Or if I want to put it simply in terms of formula which was taught in the lecture, it is going to be something around, how is that formula looks? Does anyone know? It is going to something look like GME into RE plus 2H divided by RE into RE plus H. But you cannot directly use this formula. Can anyone tell why? Basically, this is how it comes, but this is the formula given in the lecture, but you cannot directly use it, or with some modification you can use it. Yes,
So because that was assumed that this formula has been derived using launching it from the surface,
exactly. Wonderful,
but we are using it from 15 kilometers.
wonderful, wonderful. Yeah, you guys are some bright students. You guys are easily getting the point. It's great to see this. So this is, main thing is, this is for launching from surface. For launching from surface. Let's say if I want to use this, how can I modify it? See who answers this. Let's say if I can write it down, v naught square is going to be 2 gme. V naught square is gme by re plus h plus 2 gme into square root of re plus 15 and re plus 500 square dr. Right? Let's see if we can reduce it.
Sir,
So
we can replace RE from RE plus 15
we can replace re to re plus 15, and how about h?
and H equal to 485 kilometer.
Okay, okay. I hope everyone understand what she is telling. So for yeah, we'll see that. Let's see. Um, how can we do this? Let's say uh, GME by RE plus H plus 2 times GME into 1 divided by, I guess it's RE plus 15 minus 1 divided by RE plus 500. E plus H, E plus H. Okay. H is 500, by the way. Okay. Now,
So just a minute, I'm unable to get how this 2 came, 2 GM,
which one?
2, this 2 GM, slightly above.
Oh, this 2. Okay, I keep on making the same mistake, I guess. There is no 2, right?
There will not be a 2.
Okay, okay. Very good. All right. So now I think it's fine. Oh, how do we reduce it further? So we have GME into 1 by RE plus 15 minus 1 by RH plus M into V naught square. Is that correct? Let's see.
Actually,
Yes, Akhileshwar.
I think that 2 was there because of that half MV square thing. I think my bad.
Oh, okay.
We did made that 2. Okay.
Oh, this one too. All right.
I had that 2
Okay,
when
then
we took it. Okay. We multiplied both sides by 2.
okay.
Got it.
Okay. So how else we can simplify? This part and this part are same, right? This. Okay. So let's see. GME by RE plus H plus 2GME by RE plus 15 minus 2GME by RE plus H. Mm, This I think you can replace it. This and this you can subtract, and you can write this as 2GME by RE plus 15 minus GME by RE plus H. Now, how can we take that? Let's see. We can take GME out. Okay. Uh, and this becomes 2 by RE plus 15 minus 1 divided by RE plus H. Is that correct till now? I hope it's correct. So what we are interested is, let's see, if I want to replace RE to RE plus 15, then what do I need? I need to take divide by RE15 outside. Then what I can do, GME by RE plus 15 into minus, if I take RE, I'm sorry about that, if I take RE15 outside, what does it mean? Then I can multiply by RE15
Yes.
divided by RE plus H, right? And what we are interested is, let's see, let's multiply this. Then this becomes GME by RE plus 15 into 2 times REH minus RE plus 15 divided by RE plus H. Okay, this can be replaced as RE plus 15 divided by RE plus H, and 2 RE minus RE becomes RE, and 2H minus 15, 2H minus 50. Okay, so this is my velocity requirements. You can directly substitute the formulas and you can get it, but I want to be cautious over here. So how this is different from the other formula, divided by RE plus H, right? Right. And let's say if you just replace GME into RE plus 2H by RE into RE plus H, is these two same? If you just replace with RE as RE plus 15, then what happens, denominator everywhere RE you will replace it by RE plus 15. So here also what happens, you will replace it by RE plus 15, and everywhere H you subtract by 15. Then what happens, this becomes 2H minus 30, right? And this becomes RE plus 15. So plus 15, this gets subtracted, so it's going to be 2H minus 15. So this is right, so numerator would be right. And if you replace with RE plus 15, here also you will replace with RE plus 15 and H minus 15. Okay, this will also give you the same results. Okay, is that clear? Which velocity you guys are getting? Here you wanted to replace like RE dash and H dash, RE dash, RE dash, H dash, where RE dash is equal to RE plus 15, okay, and H dash is equal to H minus 15. So let's calculate what is the velocity requirement here, what is the velocity requirement here.
So 8.17 kilometers per second. For this, it was 8.18.
8 point
18 for this one.
for this one.
Yes. For if you're launching from ground, it was coming 8.18, and for 15-kilometer height, it is coming 8.17.
I mean, did you make these adjustments? RE plus 15 and H minus 15.
So without the adjustments, it's 8.18.
Okay, without adjustment, it's 8.18, which is also useful. We are going to anyway wanted to calculate that. So let's say from launching ground, okay, Akileshwar saved our time. Launching from ground, launching from ground to 500, right?
Yes, sir.
The velocity requirement is 8.18 kilometers per second. And if you do this, how much is it coming?
Sorry, 8.16.
8.16. How about this one? This will also will be 8.16. That's what we saw, right? Is everyone getting
It does
8.16?
not have any change because
Ha ha ha. So you can modify the formula also, and you can get it. So it was we just confirmed that whatever Tanisha said was right, right? So what we can do is, it's always better to derive this formula. uh, at this point it might be easy, but as it becomes different orbits, you may need to it's always better to go from fundamentals. So sometimes it's easy if we just remember the formula. It's just for remembrance. That's what you should keep in mind. So anyway, from here what we should understand is, if we launch from 15 kilometer, it's 8.16 kilometers per second. And if we launch from uh, the ground, it is going to be 8.18 seconds. It's not very big, but it is still, you know uh, a improvement. That's what we should say. Okay. So that is why, if a velocity requirement is going down, what does it mean? So what it essentially is going to,
so lesser momentum required.
the momentum requirement.
Lesser impulse is required.
Yeah, so whatever you guys said at the start of the class, everything is going to get, everything is beneficial. So for example, you will save fuel, right? For example, or with the same fuel you can increase the payload capacity from there. Fuel you can increase the payload capacity, which means uh, you may need to or you can even increase the orbit. Let's say from 500 kilometers, if I want to 520 kilometers, then it is beneficial to launch from here. So saves fuel. And what are the other things you guys were telling? Lesser momentum, lesser impulse, and all these are advantages if you do it from there. So this is the total velocity requirements. And yeah, so if you launch from ground, it's going to be around 8.18 kilometers per second. By the way, this velocity requirements, it's actually uh, it's actually independent of mass. So, for example, if you want to reach a lower Earth orbit, it's going to be around like 8 kilometers per second, 7 kilometers per second, around that. Let's say if you want to reach Moon, uh, for that you require around like 12.11 kilometers per second. The delta V you require is actually 11 kilometers per second. This Vt is what we call it as delta V. Delta V because from launch you will have 0 meters per second, and from 0 meters per second to uh, 8.18 kilometers per second. But one thing is missing here. Can you guys guess what is that? This is the total velocity requirement we are telling, but we didn't account for one thing. Let's say we are launching from 15 kilometers, something we didn't account for. Does anyone have an answer for that? Let's say if I go back to the question, let's see if you can guess it. So at the start of the class, you guys even asked a few questions about it. What is it we missed? You guys are so silent. There is this line, right? We can assume cruise speed of aircraft is altitude is 220 meters per second. So I am launching from aircraft, and aircraft is at 220 meters per second. And how is that going to affect? Any guesses?
So it will probably help us in the orbital velocity part, I guess.
Okay, but the orbital velocity, gravity, everything is added together as a total velocity requirement, right? So,
Yes, sir. But so we will have to the total velocity with which we will have to launch it will be less because
exactly.
already we have a small component as the cruise speed.
Right. So basically, uh, what Akhileshwar said is right. So what the ideal velocity requirement? So for our mission, from 15 to 500 kilometer, it's not going to be exactly at 8.16 kilometers per second, but it is going to be minus of 0.22 kilometers per second. Because we already gave, uh, you know, uh, 220 meters per second. But do you guys think that it's just simply minus? Should I just simply take the velocity requirement I require and subtract it with the initial velocity? Or is this correct? Come on, feel free to guess. Even if it is wrong, it is fine. No problem. It's correct or wrong?
So I guess it is wrong, I think.
Wrong.
So because cruise speed is actually the horizontal component in the velocity, but
Okay.
its initial that we're calculating is the initial vertical component that we will give, so that the body has sufficient momentum that after reaching the altitude it transfers its momentum into orbital speed. So
Okay.
I think 2.22 kilometers per second must be subtracted from the orbital velocity requirement.
Okay.
So
But
that will be
Yeah, that is fine. But one thing I want to make sure here is this velocity requirement is not. It's not like s- I initially start at 8.1 kilometers per second and it will directly go and reach that orbit and it start revolving, right? It is not like that. I initially do not give 8.16 kilometers per second, right? So as I started the lecture, this velocity requirement is just a uh, uh, symbol of energy required, right? It is not really the velocity with which you launch the rocket. It's not really that. You understand? So this velocity requirement is just the delta v, how much I should, you know, what is the delta v I require? Because as we discussed before, we are dealing with joules, right? Megajoules and gigajoules, and dealing with those is uh, very difficult, and that's why we are using velocity requirements, right? And that I need to make sure. I guess there is no doubt in that. So if I'm launching with 220 meters per second, which means I already have some energy. It's not like my initial kinetic energy is zero. I have some energy. So then my energy calculation, from which the total velocity requirement I'm calculating, let's say we call it Vt square. This is the energy requirement, right? Which translates to velocity requirement. It has nothing to do with we need to subtract or add. We should not think it like that. It's just a energy requirement, okay? And this is going to be equal to the gravitational energy, Gme into m by r square integral dr plus re to re plus h plus there is this orbital velocity, right? V naught square. This is the orbital velocity kinetic energy we have to reach finally, and we already have an initial velocity which we call it Vi. Okay, and this is how you should calculate this velocity requirements. Okay, I hope it is clear. I didn't confuse you much. I mean, there won't be square root here. So let's say if I want to calculate Vt, I can again cancel this m. Yes, yes, Trit. Any questions? Okay, so um, this will be plus V naught square minus Vi square. This is how you calculate the velocity requirement, not just subtracting Vi. Okay, please understand this concept. Is it clear, or you still have any doubts? So we are basically dealing with energy.
Sir,
Yeah, yeah.
excuse me, sir.
Yes, yes.
Sir, will you please repeat that once one more time, sir?
You mean the with the initial velocity to 220?
Velocity requirement, sir. Finding velocity requirement.
So velocity requirements is a velocity requirement is not really the velocity we are dealing with. We are dealing with energy. Okay, how much energy I require. So this all it's a conservation of energy. Okay, so how much energy I need to go from 15-kilometer altitude at 220 per second. And this is the velocity which I am moving to reach an orbit of 500 kilometer, and I have to move at orbital velocity v naught. So basically, you are trying to find the energy. So from initial energy, which is uh, so basically this is re plus 15 to re plus 500, right? So basically from 15-kilometer altitude, at 15-kilometer altitude I have some potential energy, and the potential energy is going to be m into mgh, right? The h should sorry, 15 kilometers at that altitude, and also I'm moving in that altitude, so I have some kinetic energy of mv square, right? And from there I want to take a satellite. So if the aircraft is moving, rocket is moving with the same velocity. If the rocket is moving at the same velocity, then satellite is also going moving at the same velocity at 15 kilometers. Basically it's cruising, right? From 15 kilometer I have to reach 500 kilometer, and at 500 kilometer I have to go to orbital velocity v naught, right? So what is total energy I require from here to there, and from that energy you calculate the velocity requirements. So this is the concept, okay? So its velocity requirement is a kind of energy required. It's not really the velocity which we used to say in physics. Is that clear? Or you can say it like the energy required for it to uh, so whatever the energy you have, uh, let's say if the satellite is rest, and if you want to reach uh, a velocity of vt, how much energy you need is what these the same energy you need when you move it from the altitude of 15 kilometer to that kilometer. I hope I didn't confuse. I understand there is a lot of things. Let me repeat once again. Okay, so you need some energy uh, from going from 15 kilometer to 500 kilometer, and at 500 kilometer to stay in orbit you need some kinetic energy. So there are two things. One is potential energy you need from 15 kilometer to 500 kilometer to move from 15 to 500, and there you need some orbital velocity which is some v naught or vo. Now at 15 kilometer you are not simply standing, though your velocity is some 220 meters per second. So that energy is already, you have that energy already, aircraft already given that energy to the satellite. So the remaining energy only you need to spend to reach there. Okay, so basically it's not so we can write it like, it's all energy conservation, please understand. It's all energy balance. So at 15 kilometer altitude you have some potential energy, and you have half m vi square, which is a kinetic energy. And now this is this is the energy you have, and then you are going to another state. This is at 500 kilometer. Here what is the energy you have? You have potential energy of 500 kilometer, and you have half m v naught square. Okay, this is the kinetic energy you have. So this is the total energy, and in order to move from here to here you have to give some energy, right? This is the total energy requirement for this, and this energy, if you just equate it to half mvt square, and you get this vt, right? This is the delta v we are talking about, or in other words, this is the energy to uh, energy required to accelerate, or how do I say, accelerate mass m to velocity, uh, accelerate mass m from 0 to velocity vt. Okay, that is what this means. Okay, and you are trying, instead of dealing with energy, I mean this has nothing to do with what is the velocity here or here. Okay, okay, you're just finding how much energy I need, because that is the energy my rocket has to give, and how we are going to give is what we are going to see in the subsequent weeks. But I don't want to say every time in terms of energy. Instead I want to say in terms of delta v. And how do I calculate delta V? Delta V is telling that as if I'm in a zero state with zero velocity at zero potential energy, and I'm getting accelerated to some velocity, and the energy required, if the total energy required is same, then I will reach this velocity, and that velocity is called the velocity requirement, or that is called delta V. Okay, that is what we really mean here. So velocity requirements is just a representation of energy. That's what I wanted to convey. So this definition has nothing to do how we are going from here to here. Okay, this VT doesn't say anything about VI or V naught. It just talks about energy. If I say I need 88 kilometers per second, then means I need some energy. You can directly translate it to some energy for a mass. Okay, is that clear, or did I confuse more?
No, sir, I understood now, sir. Thank you, sir.
Okay, anyone else have the same doubt? So basically you need to follow this equation since you have initial velocity, and you need to find the total velocity requirements. Okay, so if anyone have found it, you can give me, I can write the answer here and I can post it. If not, I will leave it up to you and you can find it and give it to me. Okay, all right. It's I took more time, 8:30. So if you so usually how I will do is I will take this class for like an hour or so, and I will leave an hour so that you can ask me questions. So we still have half an hour. If you have questions, you can ask me. So I would like to revisit few questions. I guess about flame velocity and burning velocity. Vaishnavi, are you here? Yeah. So what is your exact doubt about flame velocity and burning velocity, Vaishnavi? You are thinking about the frame of reference. Okay, what is the difference between them? So basically, the flame velocity and the burning velocity. I have you taken any combustion course or something? Do you know anything about flame velocity and burning velocity? So basically, what they will tell is, let me explain you. I think professor explained in terms of frame of reference. How do we change, right? Um, yeah. Anyway, so what I will, how can I explain this? Let's say you have a in during Diwali we used to play with this crackers, right? So we used to have this uh, sparkles, like electric sparkles. I don't know what it exactly means. So let's say you have something like this, right? So and this keeps on, so it keeps on burning. You light it up here and it keeps on going down, right? And yeah, so I hope you guys can understand. So what happens is, when you are when you are holding it in your hand, and if you are seeing it, let's say we call this as flame. Okay, let's say we call this as flame, and this is going to keep on going down. Okay, it's going to keep on go down. And what exactly happens is, what is the, let's say if you want to calculate the flame uh, velocity, I don't know exactly whether flame velocity or burning velocity. I think it's a burning velocity. So let's say if you want to calculate the burning velocity is nothing but how much it has burned, right, from here to here. So it's going to be like initially I'm at this position, let's say x1, and finally it will be at x2 position. So basically it is like x2 minus x1 divided by total time taken, delta t, right? This is what the burning velocity, but in which state? It's in your reference frame. You are standing and seeing the things burn, right? This is the reference frame from outside. Now if you look at the flame, if you see what happens near, if you sit in the flame, let's say if you sit in the flame, what happens? Say if you sit in this flame, this is the flame you are in, you will be sitting here, and what do you see? You will see some crackers entering. Since you are sitting, the flame is going to move down, but you will not know you are moving down. What you will see is, you will see some crackers coming to you, and you will see some uh, sparkles going out, right? So it will come at some velocity v1, this will go out some velocity v2. Okay, you will feel like you are stationary and you are at rest, but you will see something coming towards you and something leaving you. So this v1 is what we call it as flame velocity, which is coming to you, unburned uh, mixture coming to you, right? And if you are in the frame, if you are in the lab reference frame, or if you are holding in it and you are seeing it, then the flame moves down. That is a burning velocity. So there is a difference, just because it's a difference in frame, basically. And these two, um, will it be really same? uh, Sometimes it may, sometimes it may not. It depends upon the experiment we are doing. For here, it will remain same, because whatever the flame moving down is the rate at which this is provided. But in any some combustion experiment, if you see, there will be a strand, and there will be a liquid filled, and they will ignite it at the top. What happens? The uh, gases coming out of the velocity will be little higher, and the flame going out will be slower, because gases have low density, and so it moves out with higher. Basically this v2 will not be equal to v burning, okay? Because gases are less dense, so you need to conserve the mass, right? So this v2 will not be equal to v burning, or in other words, uh, v2 v1 will be equal to minus of v burning, something like that. V flame will be equal to minus of v burning, because from flame you will see it's coming in, so it's minus, but v burning is going down, right? Like a incense. What do you mean by incense? Yeah, incense sticks, you mean, right? So basically, actually, you no need to worry about all these things now. It's also currently it's not needed for you, but you need to know what is the difference when you go from one frame to other frame. So from here, you are holding the stick in front of you, and in that you will be sitting on the flame, when it regresses. Okay, so what are the different things you will see? That is what you need to understand. I hope that answers your question. Sure, Archana. I will be sharing the notes as soon as this class ends. You should be able to access it from the, your NPTEL class forum. So the other question is, Somasiva, are you here? You have to calculate landing position of a rover if the planet is continuously moving. Okay. I think Somasiva left. All right, we'll address that question later. Uh, okay, Crimson is asking, I got disconnected. Can you explain again? Crimson, are you here? Crimson, which one you want me to explain again? Yeah, I explained. Okay, good. So, any other questions? Does anyone have? You wanted to discuss something, or is that clear what we thought, or any other concepts you are unclear of? Oh, okay, sir. How does side real occur? Okay, it's a nice question. So, mm, let's see. So, do you know this famous question from? I guess it's they asked in some SAT exam and all. So what they asked is, so there was a coin, okay. So I'm just trying to explain it in a different manner. There is a coin, okay, some coin one, and there is another coin two which is equal in size. Let's change it to, okay. This is C2. Let's assume that radius of C1 is equal to C2. I guess it's more or less same anyway. Now I'm telling that currently I'm marking this position, okay. Now I'm asking, let's say if I revolve this from here to here, how many rotations I made? How many rotations C2 made with respect to its axis? If you are able to answer this, you should be able to understand sidereal also. So there are a lot of videos you can look at in YouTube. I'm not going to answer this, but I'm going to directly go into your sidereal, how it is happening. So you are usually the sun is somewhere here, okay, okay, and you are at Earth. Let's say you are standing here, okay. Now, uh, at so at this point in time, your the sun. So sun from your view, it is directly upwards, right? It is just top of your head. Now, after one day, what happens again? It comes to your comes to the top of your head, and that time is going to be 24, and actually that time is not going to be 24 hours, and that's going to be 23 hours and 56 minutes. So the reason is, if you since you are when this rotates, right, when it completes one rotation, sorry, yeah, when it completes one rotation, it also moved a little bit. So because of this, the sun occurs at the top of your head a little before. And that is why you call it solar day. And for a sidereal day is actually, I guess it's exactly one rotation. And that is going to be little above that, 23 hours 56 minutes, which is going to be 24 hours. Is that clear? So you think about this and this are closely related. Only thing is that the radius of rotation and the radius of these coins are little. In the coins it's comparable. For earth and sun it's very less, so that's why we see in terms of time. These and these are very similar. I request you to, you know, uh, Go and search for this in YouTube. You will get very good explanations, and then you will be able to easily understand this sidereal concept. Okay, and we have one question from Tanisha. What is the inclination angle of a polar orbit? So it's polar orbit. It depends upon what is the inclination of your poles. So your poles actually usually shift from, I think it's around minus 11 degrees, around minus to plus 11 degrees, or minus to plus 5 degrees, around that. So your polar orbit means exactly you are going from poles to pole. So if you want to make it out, if the uh, so what is really the inclination angle? So from uh, ideally inclination angle should be zero, right, for a polar orbit. So what exactly is your doubt? Tanisha, are you here? With respect to orbital plane, okay, inclination. So, okay, I think I understood what is your problem is. So basically, if this is the Earth, okay, and these are the where poles are present, and your orbit is going to be from pole to pole, okay? And all these lines go at the straight line. I might have drawn a little badly. Poles, okay, and you have Earth here. Okay, Earth is also very bad. Okay, this is the Earth, and this is the poles. So all these three crosses through a straight line, and you have what do you call the equilateral plane. The inclination angle is nothing but here to here. So for a polar orbit, what happens? You can directly say from here, right? So equilateral plane and the polar plane is going to be at 90 degrees. So if the for a polar orbit, it is going to orbit around the it is going to constantly see the poles whenever it comes up and down. So which means the theta is going to be 90 degrees. Does that answer your question? Okay. Uh, and then we have Shruti asking, how do we calculate impulse when only mass and velocity are given? So, I guess it's based on your assignment question, I guess. So, with mass and velocity given, you can only calculate momentum. You cannot calculate impulse. So, impulse is nothing but rate change of momentum, right? If I'm not if I'm right, impulse is nothing but change of momentum. So, you may need to read the question carefully in order to answer that question. How do we calculate change of momentum? Okay. And we have the telling, sir, does the pressure of propellant tank on the rocket is greater than the chamber pressure of the engine? And if yes, then why is engine needed? Couldn't we directly drive rocket by feeding pressure into the nozzle? Okay, wonderful question. Uh, so, drive the rocket by feeding pressure into the nozzle. Interesting question. So, Teerth, um, uh, for example, let's say take a liquid propellant engine, liquid rocket engine. Okay, in liquid rocket engine, you will have a tank, and you have liquid present. Okay, and mostly what happens is this liquid will be at some pressure, let's say some P1. Okay, and then we have pump. So what the reason for pump is to pump the liquid into the uh, chamber. So ideally the chamber pressure, there will be some chamber pressure. This chamber pressure may not be really less than P1. It's not necessary. It's not necessary. Okay, because anyway you have pump to pump the liquid propellant into the chamber. Basically this is a combustion chamber. Okay, um, and then what do you have is, let's say for the sake of speaking, for the sake of argument, we'll just say that we'll just say chamber pressure is less than P1, such that we will eliminate the need for pump, because since P1 is there and chamber pressure is less, there is a pressure gradient. If you just connect it with a pipe, the liquid propellant is also constantly going to flow inside, so there is no problem in that, right? But and then something happens in the chamber, right? What is that happens in the chamber? Any idea? And something happens in the chamber and some gases comes in, and then it gets accelerated through the nozzle. What exactly is a nozzle? Does it convert pressure energy to, okay, we have a, so combustion is happening, so we don't know what is combustion, but let's say something is happening, some process is happening, combustion is happening. Then we have a nozzle which actually accelerates the flow. So what this nozzle does, any idea, Teeth? So if you understand what this combustion does, then also understand what this nozzle does, then you can answer your own question. Basically you are right, you are thinking in a right manner. Why the pressure in the tank is very high, why don't you just put it in the nozzle and then send it out, right? Chamber, why we need to have a combustion, then why we need to add a nozzle, why not remove the combustion? So any thoughts, Teeth, or do you want me to?
Sir, the amount of thrust that comes out from nozzle gives the upward force.
Yeah, correct. But what Teeth is asking is, so the chamber pressure is going to be less only. Why do I even have the chamber? Why not I directly connect the nozzle and then get the, you know, thrust, the same thrust? Why not I don't do that? Is what Teeth is asking. So nozzle is going to give thrust, but why I need to have a combustion chamber? Why not directly connect tank to the nozzle? Any ideas, Teeth? Are you here? Okay. Any idea? Anyone else have any idea? All right, let me tell you. Uh, Basically, that is what you are going to study in your, I guess, week 5 or 6. Yeah, maybe 4, 5 or 6 you are going to study. Why we need a combustion chamber and all those things. So, just to give you a quick trailer, what you are going to do is, so nozzle is not simply converts pressure to velocity. This is not nozzle does. Nozzle doesn't do this. Okay, what nozzle does is, whatever the thermal energy you have, please note that it's thermal energy. It's not just pressure energy, it's thermal energy. It converts to kinetic energy. This is what nozzle does. The higher the thermal energy you have, the higher the kinetic energy you can get, and higher kinetic energy relates to thrust. Okay, so nozzle doesn't convert pressure energy to a kinetic energy, it converts thermal energy to a kinetic energy. Okay, and how we will see in this course. And what this combustion does is it converts chemical energy into the thermal energy. So basically, if you just directly connect the tank to the nozzle, so whatever the fuel you have, you will just send it out of nozzle. But the fuel has high chemical energy. How you are going to use it, right? It's the same question if I want to ask what happens inside a uh, you know CI engine or SI engine. We are trying to get some work done, right? And how is that work is done? So we will send air and let's say you take a spark ignition engine, you send air and fuel mixed together inside a the piston cylinder arrangement, and you compress it and then ignite it. Once you ignite it, the combustion starts and it generates a lot of gas and it starts expanding. And when it expands, piston moves down and the piston runs the crankshaft and you get the torque output, right? So from where this torque output is coming, where is the origin of this source? It's locked inside a chemical energy. It's nothing but from the chemical energy. It's inside the fuel, inside the fuel and air. Once the combustion happens, this chemical energy gets converted into a thermal energy. In this case, in CI engine case, it's a purely work done. It is getting converted to work done, and then you get the torque connected to other transmission systems, and you get the forward motion, right? But in rocket, this chemical energy is converted as a thermal energy, not directly converted into more work done, converted as a thermal energy, and the nozzle does the remaining part. It converts the thermal energy, which is available, to the kinetic energy at the exit of the nozzle. And if the kinetic energy is high, you will get higher thrust. And how to make this thermal energy high and how to make this kinetic energy high, all these things is going to depend on your fuel. Okay, depends upon the fuel and oxidizer and how the combustion happens inside the combustion chamber. So that is why we have a combustion chamber, because you have additional energy, right? So let's say in a spark ignition engine you send air and fuel inside. Why not let that air and fuel push the piston down? It is not going to happen, right? Combustion has to happen inside, then only you get work done, right? The same here, you can do it, but the thrust is going to be very less because you didn't harvest the thermal energy, which was harvest the kinetic energy which was inside the fuel. Is that clear, Tirth? Was that your question you were asking? It's actually a wonderful question. Okay, so one thing you need to notice: nozzle not just converts the pressure to kinetic energy. It also requires. It's not like you if you have a higher pressure, you just expand it, right? You in addition you also need to have higher temperature. So if you have a higher temperature, then you are going to get even more velocity at the exit. Maybe what you can do is, in order to understand more about nozzle, you can look at the compressible flows. Anyway, we will also study the nozzle here, maybe in week 3 or 4. Okay. um, at that time it will be more clear what is the purpose of nozzle exactly, and what nozzle requires in order to make it work efficient. All right. Is there any other question? Should I leave it? Once shared a jam file, but I'm not able to access. Once, do you want to ask anything? All right, no problem. If there are any questions, you can stay back and ask. Uh, if not, we will meet next week. Next week, same time. Thank you.
Thank you very much, sir.
Thanks, Sakilesh.
Thank you, sir.
Thank, thank you. Thank you, Tanisha. Thank you, Satrak. I don't know, maybe spelling very badly. Thank you.
Sir,
Surani. Surani.
uh, we can say like minus of momentum is impulse.
Uh, why?
Mm, because it can be minus, I guess. I tried
Why minus?
the assignment, like,
Momentum is momentum.
yeah, momentum can't be minus, but impulse maybe.
You have to figure that out. I
Ah.
cannot reveal the answer for you. But you should just simply understand what is this momentum and what is impulse. What is the difference between them? Okay. If you understand it, you should be able to answer that question.
Okay, I will search it.
Sure. Any other question? We have why do asteroids don't have orbital path like planets? All right, good question. Shruti, are you here? Did she? Okay.
Yes, sir, I'm here.
All right. So usually, what happens is asteroids are small objects in the. I mean, comparatively speaking, of course, they are large, but compared to the planets and other stars, they are very small. And what happens is they are. Uh, in fact, even planets doesn't have proper orbital path. If it is elliptical orbit, doesn't really stay in elliptical orbit. It always have a wavy kind of orbit. The reason is all this elliptical orbit, circular orbit are coming from two. We'll consider only two bodies. One is Sun and there is Earth. And what we do is we will say that Sun's gravity is get only acting on the Earth. But what happens? Earth experiences gravity from Moon. It experiences gravity from Jupiter. It experiences gravity from all the planets surrounded by it, all the stars surrounded by it. So, ideally speaking, the large amount of gravitational force may come from Sun, and because of that, it orbits around the Earth. But ideally speaking, you have a lot of other planets and other stars, which is going to keep on acting its gravitational forces on Earth. So Earth is not just reserved to Sun, right? It can the gravity can act from every other object around it. So that is the reason your orbit will not be exactly elliptical. It can go however it wants. So it goes into a, if you consider more than two bodies, we it goes to three body problem, which it's a chaos theory problem, where you consider the gravity of two bodies on the third body. and which it's actually a famous three body problem, and you cannot directly derive the solution for that problem because it's a chaotic system. It can move however it wants depending upon its initial condition. So that is the reason for asteroids. It's not just three body problem, it becomes n body problem. The reason is there are small asteroids and surrounded by a lot of asteroids, and each asteroid is going to apply gravity on other asteroids. And it's not just one asteroid is attracted towards others. It's like one asteroid is attracted to all the other asteroids, and similar with the other asteroids. So that's why we call it n body gravitational problem. And it always has it doesn't have a clear orbital path. I mean, you can you can model it, you can mathematically model it, and you can come up with a orbit, and but that orbit will not be circular or elliptical as we see for planets. It will be different. So that is the reason. I think this is what you are asking for. Does that answer your question?
Yes, sir. Yes.
So
Thank you.
basically,
So
it's
you're basically saying it's not the gravity is experienced from different bodies, not
exactly.
just one body. That's why we cannot define the path of asteroid. Like it
I-
cannot be either circular or elliptical.
we can define the path, but it won't be like a
Hmm.
circular or elliptical.
Yeah.
It can
Okay.
be different paths. It can, so for example, it might go like this also. So there will be one asteroid here and another asteroid here, another asteroid here, another asteroid here. So, and then there will be sun here, and when it goes, since it gets abstracted, it will go like this, like this, like this. It can go however you want, but this orbit can be predicted. This orbit can be predicted by solving a bunch of equations, which will be dealt in orbital mechanics. If you study orbital mechanics, you will know about it. So this can be calculated, but this path depends on all the bodies. It depends on a lot of bodies. That's why its path is not well defined, you can say.
Sure, sir. Thank you.
Next one, tomorrow. Will you share 8 pages of today's presentation? Yeah, sure. So I will be posting it in the Google Drive, and that drive will also be in that Google Sheets, which you can access it from the forum. So I will, maybe by tomorrow you should be able to access it. Right. All right. So if there are no more questions, I will stop the recording here. And